Today, we're going to look at how to design the gear train. The gear train is the part of our system that transmits the motor power to the wheels. For now, we'll assume that all of the power of the motor is transmitted to the wheels. None of the power is lost. This isn't technically true because there is always some power lost when transmitting power. But we'll assume that we already accounted for this in our damping tests that we did previously. Although the power will stay the same through the gear train, the torque and velocity will not be the same. Now, we know that power is equal to torque times velocity. So, if we design a gear train so that it increases the velocity, then that same gear train will decrease the torque. And vice versa. If the gear train decreases the velocity, then the torque will increase. We will start by deciding what we want the gear train to do. Do we want the gear train to increase the velocity and decrease the torque? Or do we want the gear train to decrease the velocity and increase the torque? In the last assignment, we figured out what range of motor speeds we could use and still get the required 8 watts of power from the motor. And we also learned that in general, operating at a faster speed is more efficient. Until we get too fast, then the efficiency drops off. So let's suppose that we've decided to operate the motor at a speed of 710 radians per second. And we found out from our torque speed curve that the motor has 0.0114 newton meters of torque available at that speed. Let's start by checking if this speed is too fast, too slow, or just right. Suppose that the wheel here is turning at 710 radians per second. That's what would happen if we directly connected the motor to the shaft of the wheel without a gear train. Could we figure out how fast the hoverboard is moving in meters per second? Sure, we know that V equals omega R. We haven't yet picked a radius for our wheel, so let's just plug in the numbers that we have. We know that V has to be 3 meters per second from the first week requirements. Then I put in 710 radians per second. That gives us a wheel radius of 3 over 710 meters, or about 4 millimeters. That's a super small wheel. So what does this mean about the speed? Is our 710 radians per second too fast or too slow? Let's plug in a more reasonable value for the wheel radius, something like 0.1 meters. In this case, omega would be equal to 3 divided by 0.1, so omega is equal to 30 radians per second. So our original 710 radians per second is way fast. We could slow it down. As we know, slowing down the speed will give us more torque. So let's check the torque now. We figured out in week 1 that we needed about 0.2 newton meters of torque to move the cat up the hill. But our motor only has 0.0114 newton meters of torque available at the 710 radians per second speed. That's great. It means that we need to increase the torque, and we are able to decrease the speed to achieve it. Now, all we have to do is figure out how to design the gear train to accomplish this. So here's how the gear train works. The motor is attached to a pulley here, and the wheel is attached to a pulley over here. We'll put a variable on the radius of the pulley attached to the motor, and one on the pulley attached to the wheel, and another variable on the radius of the wheel itself. You have to find values for these 3 radii that will end up giving you the required torque and speed at the wheel. Given the limitations of 710 radians per second and 0.0114 newton meters of torque at the motor. Once you've figured that out, you now have to go find some actual parts online that you could use to build this thing. You don't have to actually build it, just find the parts. You might start by searching for the term timing belt and timing belt pulley. A timing belt is a belt that has little teeth on it, which match with the teeth on the timing belt pulleys. It's kind of like a cross between a belt and a gear. You should be able to find pulleys of different diameters that have the teeth sized and spaced the same, so that they match with the sizing and spacing of teeth on the belt also. The last thing you'll do in this assignment is to look at some other options for gear heads or gearboxes on the motor. The motor that we picked out for the calculations we did last time has a gearbox that adjusts the balance of torque and speed at the motor shaft. We could have picked some different gearbox on the same motor to get a better torque-speed relationship at the motor shaft before connecting it to the gear train. That might allow us to have a smaller difference in the radii of the two pulleys. When you do question 5, remember that changing the gearbox doesn't change the motor power. So the product of torque and speed will stay the same no matter what gearbox you choose.